four colleges students? Yes? SDBI, yes. I'm sorry. So today I just wanted to touch base on Bootloader. So it's a vast. Okay. So I just wanted to give a kind of overview and what is Bootloader and how it is kind of communicated to an embedded devices like IoTs and mobile and even server chips also, right? So to begin with that, I have one question in my mind. I'll just start with the cell phone. So this is our product, not the cell phone, Snapdragon. So we have a Snapdragon mobile version, we have a Snapdragon automotive version, we have a Snapdragon server version, we have a Snapdragon for IoT version. So let's discuss about first thing is Snapdragon mobile version. So I just have a question. When you switch on your cell phone, what do you see? Anyone? Yes. I just want to be this interactive session. Otherwise, if I speak and just listen, doesn't make sense for me to just understand where you are and how whatever I speak today. I just wanted to make sure it should go inside and just moving forward, you just think in that perspective. Anyone, can you switch on your phone, what happens? Yes? Yes, it's yeah.
So, page first.
Okay. Bootloader so that others can understand. Yeah.
Practically you page, and whatever app you want to open, you open this.
Okay. That's it. Okay. Anything other than this? Yes, go ahead. Okay. Then what else? Your WhatsApp comes, you start chatting. Right? Okay. What else? Anything? Yes. Yes. Go ahead.
When we start the mobile use from a power off state, it comes to a boot screen.
Yeah.
Powered by Android and all the devices. Okay. Then it takes time to load and then it will be.
Absolutely. So, if I go and recruit engineers in campus, if an answer comes from like this, apps comes and screen comes, straight away I reject it. You're all engineers, right? You're all engineers. Even 10th or 7th standard student can say what happens when you switch on the phone, right? Simple. It's a kind of layman language. They explain, but much better than whatever I see today. I got the answer today. It's not a bigger problem. That's what we are going to work together. There is a gap between the industry and academia. Okay, industry is somewhere and academia is somewhere. So we need to bridge this gap by doing these kind of sessions, right? So, and also once today I speak those things, just note down those whatever the term I discuss and go back and expand those things, right? So you need to spend time, quality time, productive time to serve a thing what is required for your career to build in the semiconductor industry. Trust me, this is going to help you to build your career. I repeat the same thing in semiconductors. So as I said, when you switch on your phone, let's say this phone has a core Snapdragon SoC. Out of 4 core, the master core comes out of the reset. This is what we expect. When I say reset means before switching on, it was in idle, it was in sleep, it was not powered up. When you switch on your cell phone, the power goes immediately to the core and the master core wakes up. That is the first core master core. So the clock goes, the power goes, then we start activity. Then once it is activated, the remaining 3 cores are waked up by master core. Right? So ask the remaining 3 cores, keep idle for some time. I am going to do something, then I will wait you, I will give some task to you. So once the master course comes out of the reset, there is a flash, there is a boot. I will just explain in my slide. There are the straps, boot strap and pin straps, right? So when you have a development mode, we may boot the boot from the, because the Snapdragon will be in the lab. It will support booting from the flash, booting from the whatever SD card, whatever hard disk, blah blah. So if a developer wants to boot from particular device, he has to strap it. there are two ways to strap. One is pin strap. Using jumpers, you can go and pick the location from particular device, or there is a boot strap where there is a CPLDs or some kind of a buffer which is burned, which is shorted, which is whatever, directly go and boot from this place. So I will just explain what are the boot strap and the pin strap. Then once your pin strap says boot from the flash will be external to the Snapdragon. When you open this cell phone, the Snapdragon will be somewhere else, right? There is a flash memory which is outside the Snapdragon. Then there is a connection. That's what strapping. Once the strap is established, then the master core jumps to the reset vector first. In the reset vector, we mentioned where to boot, which location to boot. So once I mentioned that as a programmer, as engineers, as embedded engineers, as a firmware engineer, you need to do all those things. Once you do that, it jumps to that location. Usually it is FFFFC. It's the end of the flash, right? So once it jumps over there, then the first instruction executed from that. So this is the bootloader beginning. So this is what you need to delete. So whenever you got time, just go and surf what is bootloader, how it is, what are the content of the U-boot, what are the stages of the bootloader, so that you can expand your knowledge beyond this. And when you put this term in your resume, at least your resume gets shortlisted for the semiconductor companies. Trust me. But you need to explain what is bootloader. Whatever you wrote in your CV, you need to explain that. So this is what the bootloader is. So I wanted to start with the first slide. As I said, so boot technology, loader, program that moves bits from non-volatile memory to memory and then transfers CPU control to the memory loaded bits executable. As I said, whatever we develop, whatever Qualcomm develops, basically the Qualcomm gives Snapdragon and the firmware and the software. When I say entire firmware and software, we develop bootloader, we develop device drivers, whatever there inside the Snapdragon, be Bluetooth driver, be Wi-Fi driver, be camera controller, whatever. So we develop all those things, which is a part of the bootloader, but not the primary. There are two types of bootloader. Okay, a primary bootloader and a secondary bootloader. The primary bootloader is the one where I am going to discuss today, but the secondary is a next level that we'll do in next session. So this is what the bootloader. So as I said, it loads the data from flash to RAM. I'll come to that. What is that data? Then, as I said, bootloader has just bootstrap. So it has to be strapped. How the connection between the, let's say, as I said, usually when the production, when we give this Snapdragon to the Apple, or we have tier 1 companies like Apple or OnePlus or Samsung. So they just use the flash, one device, and there is a strap. Once you switch on, that is connected, established, then you start executing the code from that. That is within a fraction of microsecond. Right? When you switch on yourself, your icons comes immediately. That's what user expect. If it won't comes, he will will not tolerate. When you switch on his phone, you want to see his Facebook, you want to see his WhatsApp. So loaders should be very fast. So why? How it is going to be happen? Because the flash memory runs in megahertz, right? Flash memory runs in megahertz, but the code is like in a kind of MB or some 640 KB or whatever. So loading will take time. Then how it's going to happen? So I will explain how it is going to be fast. So these are the whatever I explained: the boot strap, bootloader, and the prompt. So let's move on. As I said, flash memory. So it will be external to the device. A program that moves bits from flash to disk or memory and then transfers control to the memory loaded bits. Okay. I'm just giving it as a layman, it's a generic one sentence. But when you expand this, what happens? So when you switch on the cell phone, as I said, control goes to the reset vector. The reset vector is strapped to the flash. The flash contains the bootloader. The first instruction is wake the remaining 3 cores. It goes and gives the clock and the power to the 3 cores. Those are all assembly instructions, not the C. Okay. Or basically all the microcontroller embedded systems are based on R. Right? So once the instructions are fetched from the flash and they said that enable the remaining 3 cores, then we don't need any high-speed devices, touch screen, Bluetooth, Wi-Fi, nothing at this moment. We need a simple slow-speed interfaces, UART, I2C. Just initialize the UART and I2C controller because those are the one where is like connected to RAM's PROM. There is an EEPROM in the RAM, DDR memory, which has all the details in that. To access that PROM, we need I2C. If I want to have a kind of console, I have to have a UART. So for development time, if you book a debugger or JTAG code, then you have to initialize the UART. So these are the small piece of assembly code where kind of a low light driver, I can say, I2C and UART driver will be initialized. Soon after these two is initialized, then it gets the access of the DDR controller. That is external to the Snapdragon. So that DDR controller has the EEPROM which has details of all those things. Speed, manufacturing, whatever frequency, calibration details, file details, all those things will be burned in the EEPROM which we get from the third party. Like Micron develops the DDR, right? So we get the DDR with that information. Once we get the DDR, we initialize the DDR because now we'll explain why the things take so fast. We don't want to execute our code from the flash. Flash runs in megahertz. If it runs in megahertz, if I switch on the phone, it will take at least minimum 10 minutes or 15 minutes to come up your WhatsApp or Facebook. I wanted to move my code from flash to DDR. So it is like the DDR controller and calibrate. Already calibration is done in the, when I say calibrate, this is a new word, you need to note down what is calibrate because each digital has an analog part in that, right? So analog part is a flaky, analog part has its own characteristic. To work the analog part to sync with digital, we need to calibrate that. Like all these high-speed devices, as I said, DDR, PCIe, Ethernet, USB, these are all has a file. Glue stick is, there is a digital module, then there is a file module that will be attached to that. So get those data and initialize the DDR. Once you initialize the DDR, relocate the code from flash to DDR. So copy entire thing, whatever there, primary bootloader, whatever blah blah, from flash to DDR. Then the master code immediately jumps from flash to DDR, then start executing wherever it comes from that. This is what the cell phone Snapdragon started. So as I said, this is the kind of wherever memory reaches all your data, then moves to the DDR, then executes. If you have any question, you can ask instead of waiting last. If something is there in your mind, you can ask and clarify. Any questions at the moment? You have to be, it should be interactive first. I hope you have some questions. If you keep idle, it will be lost for your career. Yes, go ahead.
So before bootloading, there is a pre-check, sir. So where it checks if any external hardware are connected. Then the bootloader programs takes place. So may I know what triggers the bootloader to happen or it can happen sequentially?
The first thing is when you switch on, as I said, there's a boot strap or spin strap which is connected to flash. There is no trigger. I hard-coded. When I switch on, the program PC has to be loaded into the reset vector. That reset vector, as I said, example FFFFC, that is mapped to the flash memory. That flash memory has a data, and data is start fetching from the CPU, which executes that data, all the assembly code. So this is how it is. So there is no,
kernel in the operating system.
Kernel is not coming into picture right now. There is no initial RAM disk, there is no kernel, there is no Windows, nothing. So that comes later on. Initially you have to initialize with the bootloader. That is a minimal thing. As I said, slow speed devices, I2C, UART or some other which is required at this moment. Once I come to that, once that is done, then the remaining thing will come. But till we are not on that level. Is that to answer the question? Yes. Anything? Let's move on. Okay. So as I said, that is a CPU reset. As I said, reset vector is whatever 2 followed by 7 zeros. It may be something else, as I said. So that is there in the bootloader. To answer your question, the first is bootloader. This is a memory map. This is kernel image. Then root file system. Everything is there in the ROM. ROM may be flash, ROM may be SDRAM, ROM may be SDD. Whatever. Right? So everything is burned over there. And as I said, when you switch on, goes for the reset vector, immediately loads to strapping, then executes one. Once it is executed limited bootloader, then the boot 2 jumps to SDRAM, maybe DDR or RAM, whatever it is. Right? Is it loaded? Then start this program. Again, CPU jump from ROM to RAM, then executes. Once the primary bootloader loads, the secondary bootloader loads, then your kernel comes, Android comes, whatever, cell phone, or in Windows comes. Windows has a different bootloader that is, I don't want to mix right now. I wanted to just only talk embedded device driver, embedded bootloaders, embedded controller bootloaders. So once it jumps to the DDR, what else? What are the things happens? Before I jump in, once the control goes to the DDR and all other things, there are a lot of information, lot of initialization done. Like minimal thing I can say, to load my kernel, what are the interfaces required? To load my kernel, what are the interfaces required? Maybe I can put even what USB driver, Wi-Fi driver, Bluetooth driver. Then if it is a quad core, it is a much complex CPU complex. CPU is a kind of bus, high-speed buses surrounding the CPUs, cache memory, cache controller, right? So there will be a kind of hierarchy of buses. Axis bus, which runs in some gigahertz, then AHV bus, which is runs again lesser than the whatever gigahertz, then APV bus in megahertz. So we need to have a controller for each and every buses, right? So initialize all those buses, initialize all the cache controller, initialize the high speed whatever peripherals required at that time, initialize those things. Those are all C code. Okay. So the bootloader has a mixed language. Initially it is assembly, that is RISC based, ARM based, all the instructions set. Then there is an interface, how to connect, how to call C calls inside the assembly. So it's a mixed once. Initially all, as I said, minimal assembly, then it goes to the C. Then C has all the luxury. You have a device driver developed in the C, then all the drivers will be initialized from the DDR. So what is, once the DDR is initialized, then you have there is a kind of, again in embedded, I don't want to go that. If non-embedded, if the DFDP, because it's non-embedded, it is a server, then the OS will be big enough. They don't want to burn the flash. They don't want to put in hard disk. There may be somewhere else that remains for server. So once your Ethernet port is up, it goes and fetches the data from where else XYZ location, then loads that. But right now we are talking only the cell phone. All your initial RAM, kernel will be there in the ROM, then that is comes up, and all your icons opens, then start chatting, do whatever you want. This happens within a fraction of a second. Why? Because RAM runs in DDR, DDR runs in gigahertz. Right? That's what we go and do the spec. You want to buy a latest RAM, right? Or latest cell phone. Or I want a quad core because I need to push my power. I want a DDR which is 256 GB, sorry, whatever, 1.2 gigahertz or 1.5 or 2 gigahertz speed, whatever. Or I want to all this, make this list and go for the market depending on your requirement, buy a cell phone. Ultimately, cell phone has all these details which there in the code. So let's move on next. Then how, what is the use of this bootloader? Why, why we need a bootloader? Instead of bootloader, directly you can load a OS, right? Or you can put the OS or whatever initial RAM is. Why the bootloader is required? So, to answer this, initially, as I said, all these high speeds are initially talking in a language where it should be feeded very fast. And all this, whatever skins, to do that, hardware is a kind of, CPU is a hardware, we need to give a kind of muscle, all those things. To do that, we need to have a kind of smaller minimal amount of code where we need to utilize, like I said, like AXI buses, ATV buses, or AHV buses, or cache controller. We have to have a loader, bootloader, which has a kind of gives immediately oxygen to the feeding to the processor so that it's hungry. I want to execute the instruction. Give me all the instructions. So feed it. This is what initial bootloader or bootloader, which helps for doing those things. And also, ultimately, as a layman language I'm telling, but as a kind of hierarchy, we have to have a kind of initialize first thing which is done only in the assembly, or that is in bootloader or in bootloader. Then C code, that is general. So those C codes are all assembly or all OS are written in C code. So that's what C code comes to. That's what we need in bootloader. That is a universal bootloader. Right now, U-boot, which is there for the embedded system. What is the use of this U-boot? Why it is there and why? Who does develop this? It's a open source. It support all the embedded controllers around the whatever, all IoTs, cell phones, then your this thing, IoT, cell phone, and one more thing is what I said is whatever embedded controllers which has a kind of independent thing where gadgets where all this embedded controller gadgets has embedded controller where the U-boot supports. Whatever the supported cores like ARM, PowerPC, RISC, whatever there under the umbrella, all it supports all those things. So I'll come to that. Whatever this is open source, started in October 1999, all those things free software. The website is somewhere. You have to go and get the source code. And the source code is so big, you have to chop it according to your requirement, code it as per your requirement, then code easy as debug, then supported architecture of PPC, that's PowerPC, ARM, MIPS, x86, Motorola, and other whatever sub-processors. So currently it supports 216 boards. When I say board means all the development boards. Just keep on adding. Whoever has their own board, their own thing, they have to take the bootloader from the open source, chop it, code it, and submit back to the open source. Then whatever you have a board, that board gets added. This is how bootloader works. So why initially this is used? In a kind of once the SoC comes out of the fab, you have to have a kind of debug commands where you need to run some commands, right? So as an engineer, I said I don't want to go as an end product right now. Once the product comes out of the fab, so you need to test it. There will be a development boards where it's a socketed board. You can open the socket and put the part and switch on the board, then start testing. How? It will be a USB or UART COM port which is connected, and when you switch on, whatever that comes on the console, which is booted from the booted from the flash, and all the information comes to the UART. Then it stops at one point, like debug prompt, where you can run the commands. This is what the useful of bootloader. Otherwise, we cannot develop whatever we wanted to develop for my own my own customized board. So as I said, if you have customized, if you have your own development activity, or if you have new innovated some kind of design, so you want to test that, so get the board and put this information into the flash and switch on. All the things whatever I said executed, then the prompt comes. From the prompt, test your own masala in that, whatever design you have added, right? And when you design, when you add that design, you have to stitch it. The SOC level things has to come into picture, right? Existing Bluetooth, we will be taking existing Bluetooth, existing Wi-Fi, existing USB, existing whatever other interfaces. So how it interfaced, how it is worked, how it is stitched properly, whether it is coming or not, working or not. So test those things. Those are all commands written on the bootloader prompt. So run those debug commands, then see whether all the test case or whatever command is a kind of, one command is a test case, memory test, yum test, right? Which is DDR test. So like that, I2C test, UR test. Do all those tests on this commands. This is what I expect. So these are the commands which is supported. These are the UR hyperterminal that is going to work forever. Now also moving forward is going to work because it's very slow speed and it works with all the things. There is no way hyperterminal is not going to work. That is the kind of thing where Brahmastra for the debug engineer, hyperterminal is the one where he uses initial debug activities. So this is information comes, whatever you when you switch on, all this is loaded in from the flash. Then these are the commands which is supported by the UI. So you just go through one by one and understand what are these commands, how you need to pass the parameters. This is all programming point of view. I don't want to go in details about programming. You have to do on your own. Let's explore this. If you want to add your own commands, you can add. You can save it. That flexibility there in the YouTube. And submit back to the open source. So the way is right. Standalone programs, OS kernel images, RAM disk images, multi-file images, firmware images, script files. Apart from this also you can load the script files, which is there in Tickle or Perl. You can load those also. Those are very important nowadays. People wanted to develop fast using this Tickle or Perl, which is useful for the regression. If I want to regress remotely, if I want to run weekend test or soaking test. When I say soaking means like you have to bombard your SOC with all the things continuously which work sustain with all the high temperature, low temperature, high voltage, low voltage, all the PPT testing. So you can do that using Tickle and Perl. These are the images you can load. So this is a kind of, I put this slide for activity where you want to look how to go ahead with that. Okay. Board name, let's say you bought one board which has particular SOC in that. So make that board file and copy the existing board file and modify according to your requirement. Like memory map, where it starts, and the addresses, whatever, I2C addresses, blah blah, all those things there is that one. You have a readme file, nice readme, you can go through that readme and use all detailed information. Any questions at this moment? So let's move on. Say how to compile the bootloader. So simple, make file, go and modify the make file. Basically, there is a directory and hierarchy structure for all when you get the bootloader from the open source. It's a big thing. First, you need to understand which folder I have got. So then there will be a kind of command line, make command, commands, make how compiling the commands, use this, and which will compile the entire bootloader only particular to your platform. So those are all information will be there in the make file. So you need to understand make file, you need to understand command, how to run the compilation in Linux, and cross compiling, that is ARM or cross compiling, how you need to make that. So you need to just expose those things before you start. And how I can cross compile for ARM, PPC, RISC, those all details are there, then you need to understand how to do that. So this is a place where you need to get source code, and it has a version number, sub-version number, patch level, all those things. Whatever patch level. So the open source guys keep on adding stuffs in that. They release the patches. So note down those patches. What are the things added in that particular patch? So understand that and check whether it is working or not. And to submit the bootloader, it should be thoroughly tested and reviewed by a third person. There is a authentication done. You cannot open. We cannot go and submit it. It will be reviewed by the open source particular group. Then, if they say go ahead, then go and submit further. So these are the supported platforms and the number of ports, current status. So you may add a whole thing also. Moving forward, design principle, easy to port a new architecture, new processor and new boards. Easy to debug as a serial console or to test it as soon as possible. Features and commands configurable as small as possible, like not like your Windows BIOS server loader, it's a kind of small and reliable. Works like hanging thing is not going to happen. It will be every time you switch on, it works. Like PC may hang, Windows may come later, but here it works. So although you can support any OS standalone, and you boot includes many features, all whatever bootloader, Linux kernel, initial RAM disk, all those things like this is required. So each and every OS like Linux or Android has a Linux kernel as well as initial RAM disk. RAM disk is the one where you can put all your drivers and other things. Kernel has all the flexibility to use the GUI touch. So these two are required. Once the bootloader is done, then the kernel and RAM disk both are required. So I have also built some of the commands. These are the commands, as I said, simple memory test, this is a M test, memory dump. Let's say you can directly go and see whether whatever the DDR. Let's say if you put your test code into DDR, then you can go and check where the DDR, where my test is located and what is the content. So just doing the MD, or you can go and write anything on DDR, MM. So these are all the things, and loop test like USB. Let's say if you want to test the USB or Ethernet or PCI test, initially it's all loop back test, maybe external loop back or internal loop back. So set the internal loop back bit and send the packet. So right now whatever I speak, it may go out of your this thing. I expect, because these are the things industry expect. Okay, I will go one more level down. When I say when I want to test the USB, okay, how I need to test without any OS? Simple question. If I want to test the Wi-Fi, how can I test without the router? It's a kind of independent setup where is there in the lab. So for that, each and every IP supports debug features. What are those debug features? Like loopbacks. When I say loopback means, let's say this is your Ethernet IP, okay? MAC, right? Media, which is there, which has a loop look back bit. So when I say look back is, so this is your, let's say when you zoom it, when Snapdragon is zoomed out, there's a port somewhere sitting here, and DDR somewhere sitting is, and Ethernet is here. Okay. And if I want to test the functionality of this Ethernet and till the connector level, I have to cook a packet in DDR. Think what I'm copying in an industry perspective, in a debug or initial development phase. Cook a packet, add a header and footer. The IPv4, IPv6 packets, put a header and footer and put the payload, whatever payload you want, AA55, AA5, this is standard payload because it toggles all the bits, right? So put the payload and send that packet. The packet is right now residing in DDR. Then send that packet to the port. The packet goes all the ways from DDR. The bus will be tested, right? So I can check the integrity of DDR to MAC. Then the packet goes here. It's a complex, which is layer wise, 5 layer, MAC layer, blah blah will be there. Then configure this loopback. The loopback is configured, whatever the packet sends out, TX is configured to RX. So it comes out to the RX. The TX is configured to RX. The packet goes and comes back, again lands in different location of the DDR. Then check the packet integrity. So once the packet integrity is passes, then your interface between the DDR, CPU says there is command that is tested, then the DDR is tested, then the path will be tested. This is how we need to validate. This kind of functionality is there in each and every IP. USB, PCI, Ethernet, I2C, SPI, button. So initial test development, whatever when you join a corporate in semiconductor, you will be assigned. Let's run this test case. Maybe run in the post silicon or big silicon to run that, develop that. So you need to go through the specification of this MAC, data sheet of the MAC, and understand where which is that bit and which is that location, and write that. This is what the development embedded development engineer has to do this. So that's what I said. Loop is the one where this is one example I am giving. Loop test is was this it is. Similarly, there are n number of tests. So I'll come to that in different session. The pre-silicon and the post-silicon activities. That's all will be the different process. So we'll discuss in next session. So these are the there are 1 to 4 slides of these commands. Like I just want to go through quick ping test. Right? Ping means what? It's a kind of packet sent from one node to another one. So it gives back. So that you can check the source to destination integrity. So whenever I speak now, it's a kind of industry word I'm putting. It's not academic. So industry means you have to put hands-on experience. You have to put whatever wanted to check. You have to put your hand in DDR. See, you can change it to the location, or you can put the program counter hand, change it to the program counter the way you want using debugger. So once they develop cell phone, you cannot see all those things, right? Everything is polished and product wise. It's a product, but before it comes, you have to do all those things. It has gone through that. It's a life cycle, 6 months life cycle to develop the 800 series Snapdragon, which comes out of that. So that side, till from first day to whatever 0th day call, when the system comes, when the Snapdragon comes from the fab, we start at day 0. Then 6 months. It's a conveyor belt. One after the other, keep on coming products. You have to test it, run it, test it, run it. That's what we have 10,000 employees in bank. All are doing this kind of design, verification, back-end, validation, post-silicon, pre-silicon, embedded development, device development, software development, all these activities happen. And multiple products. So let's move on. These are the other sets. So I hope you have to go through this in your free time. Just understand this, what each command does, and expand. And if you want to add your own commands, add. See, new Bootloader is open source. Download that. And already right now you have boards, Android, whatever, Raspberry Pi boards, or Arduino boards, get those boards with a reasonable price and start playing. Once you start playing, you will get involved in that. Your interest will be diverted and you will learn something. Trust me, you will get a lot of information. And with that, you can get a new word and put those words in your resume, and at the end, it may take 3 months, 6 months, 1 year, you will land inside the companies. So these are the commands. Then, this is now for your information, Read me first. What you do? Get the bootloader. Go through the read me first before doing anything. It's a big read me, which gives all the information. Go through that read me. So that's all I have today. But I don't right now. Whatever you put simple thing I said. It's a vast. Beyond this, if you have any questions, anything gets clarified, you can, I am giving my number to Madam, so you can contact me and we can discuss further. So with this, I am going to end my session. I am waiting for multiple questions for you guys. Yes, go ahead. This is the right time for you guys to ask the question.